awesome. So I wanted to begin by talking to you, even understanding what exponential growth means. Do you guys know what it means to be exponential growth? To grow by exponential? Yeah, of course, that's what everybody says. No, but that's not what it means, though. Okay. So what it means is this. It means for equal distance. So for equal distance, you grow or decay by equal factors. Okay, that's the important word there is factors. So for equal distance, I should put right here, grow or decay by equal factors. So what does that mean? And in terms of on the graph, so I think that if I show you on the graph, it makes a lot more sense. So this is the function over here. I graphed this function, a very basic one, 2 to the x. This is an exponential function. We know that the guaranteed points would be, 0, 1, and then 1, 2. No big deal. But here's what I mean by for equal distance, okay? So from 0 to 1, okay, I grew by a factor of 2, okay? So here's what I mean. If I make a little table, it might help you see it. So let's go x, and then let's go f of x. And if x is a 0, what's the output? What's f of x? 1. Very good, okay? If x is 1, what's the output? 2, which I clearly have over here, 1, 2. It's that point right there. If x is 2, what's the output? 4. And then if x is 3, what's the output? No, not 9. It's 2 to the x. 8. There you go. Okay. So look, for equal growth, I have a unit from 0 to 1. I've gone 1 unit. You right? Agree with that? Okay. And I have a factor of 2. From 1 to 2, I have equal distance, and I have a factor of 2 times that much, right? For 2 to 3, I have a distance of 1, equal distance. I've grown by 2 times that much. So do you see what I mean by that? So 0, 1, and then 1, 2, and then 2, 4. So all of these are factors of 2 times the previous amount. You see that? So for 3, I was way up here at 8, and that's 2 times the previous amount. So I'm not sure if it's ever been explained to you what it actually means for something to be exponential, growth or decay. This is what it means. So for equal distance on the x-axis, you grow by the same factor each time on the y-axis. Okay? I thought that would be useful for you guys. Are you cool with that? There are other types of base of growth and decay models, but they can all be turned into or transformed into either with a base e or not with a base e. So the ones that we're going to use are going to start with a base e. So the basic one is this: the amount that you want, or the amount that you're working with, has to be equal to the initial amount times e to the kt. So what I'm going to do now is I'm going to explain to you what each of these things mean. Okay. So this right here, this is the amount that you want, or the amount that you're looking for, or the amount that you will get. A naught, this is your initial amount. So whatever you're starting with. E, of course, is that special natural number. So that's about 2.71, blah, 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 blah. We're just going to use E for it, of course. And then we have K and we have T. We'll start with T. T, of course, is time. And it depends on the unit that you're working with. Could be hours, could be days, could be years, whatever unit you're working with. And K is your growth or your decay constant. Okay, and in many of the problems that you're going to be asked to do, you're going to have to figure out what K is first, and then substitute back in to get your growth model or your decay model out of it. So it's very important that you know what each of these pieces do, right? The A on the left side is your amount. The A with the little 0 at the bottom, that's A naught. That's your initial amount. E, of course, is E. K is your growth or decay constant. And T is time. So how do you know if you're dealing with a growth or a decay? Well, if K is greater than 0, that implies we're going to have what? Take a guess. Growth. Very good. If K is less than 0, it implies what? Take a guess. Decay. Very good. Okay, so that's how you know which one you're dealing with based off of the model. Okay, so consider this little drawing here that's been brought to us by the U.S. Census Bureau. And what we have here is a graph that represents the U.S. population from the years 1970 all the way to the years 2007. Okay? So in 1970, it's telling us that the population of the United States was 203.3 million. So this is in millions. And then by 2007, it grew to 300.9 million. What do you think it is today in the year 2014? 314, 315, 316. Well, we're gonna look it up. We'll look it up in a second. But before we do that, though, we're actually gonna use the model that we get to predict the year, to predict what the population is in the year 2013, and then compare that to Google and see how close we are. Okay? So we're gonna start by writing down what we know. The task at hand here is to create a growth model for the years 1970 to 2007. So we're going to start by saying, all right, the amount has to be the initial amount, e to the kt. So here's what we start with. And we know one of these right off the bat. What's the initial amount that we have, you guys? Well, according to the graph, it's, no, in 1970, it was 203.3 million, okay? It's not zero. So 203.3 million e to the kt. All right, now we need another point. We need another data point. And since we're being asked to make a model from 1970 to 2007, we're going to use the point at 2007. Okay? So how many years past 1970 is 2007? It's 37 years. Okay. And in the year in the 37th year, what was our population? So the amount, so check this out. This is how I'm going to relate these two, okay? 300.9 million has to equal 203.3 million e to the 37k. So do you see how I tied together 37 with 300.9 million? Do you see that? That's an important step right there. But why? Because in 37 years the population was 300.9 million. Okay? So I have to use what's given to me to create the model. So my goal, ladies and gentlemen, is to solve for k and then rewrite the model with 203.3 in it. Okay? So this is where we get good at using what we know of in terms of solving log equations. Okay? So right away, what can I do? What do you see that I could do? Well, I could divide out 203.3 from both sides. Okay? So this gives me 300.9 over 203.3 is now equal to e to 37k. And I'm going to leave that number just like that while I do this, okay? What can I do now? What we do in our homework yesterday? What we learn? Take the natural log of both sides, right? So the natural log of 300.9 divided by 203.3 equals the natural log of e to the 37k. Well, this is really nice because we know what the right-hand side of this equation is going to become. What's it going to become? Just 37k, right? So 37k is now equal to the natural log of this number that we have, 300.9 over 203.3. We want k, so I'm going to divide both sides by 37. And then this is where we get to actually use our calculator. So we'll bring our calculator up. We'll clear everything out. And if k is growth, representing growth, should we expect a positive k or a negative k? It should be positive, right? All right, so here we go. So let me show you how to plug this in the calculator. You're going to go natural log of 300.9 divided by 203.3. And then, you know what, I'm just going to push enter on my calculator first. Then, with that number stored in the last line of my calculator, I'm just going to hit divide 37 and then end up with a positive answer. Now let's go to 3 decimal places. So k would be approximately 0.011. You guys good with that? You guys okay with that part? Hello? Yeah? Alright, sweet. So, oh, wrong button. Sorry. Let's go. So k is now approximately 0.011. Did I do that right? Okay, good. So now that I know what k is, I can then go back and we'll go orange here and we'll write down the model that we're going to use is the initial amount, which was 203.3, e to the 0.011 t. And this is going to represent the exponential growth model for the population of the United States between the years of 1970 and 2007. And I'll pause right there. All right, the power of mathematics and the power that this enables you to do is we can now take our model and we can apply it to situations to use it to predict in the future. Now, it's currently the year 2014, but we don't have enough data on 2014 to actually get the predicted population yet. So I'm gonna go 2013, okay? So think about this. Before we actually plug this in and plug and chug here, we know that in 2007, the population was 300.9 million. So here's what I'd like you to do, like take a guess for the year 2013. Before we do anything, just take a guess. What do you think was a reasonable answer we should get? 314? 326? 326, 320? So 320 million. Okay, so it looks like if we get a number, I mean, why would it make you guess? Like, what's the point of making you guess right now? Yeah, if you end up with a number like 400 million or 500 million, you probably did something wrong, you know? So it's a good idea to know ballpark where you're headed. You know, I mean, you don't just get in the car and start driving, right? You kind of have an idea of where you want to go. So you kind of want to use the same logic here. Okay, so here's what we're going to do. We're going to figure out the amount of people. We're going to go 203.3 e to the 0.011. Now, time. Let's see here. 2013. How many years after 1970 would be 2013? 33? 43? Because it's from 1970, right? It's from 1970. Okay? Yeah, so yeah, exactly. So let me move this up. All right? So let's plug this in the calculator and see. All right? So we're going to say this. I'm going to go second e, which is right here. Second natural log. So e to the 0.011 and then times 43. And then we get an answer. And then multiply that by 2,000 or 203.3. Did it work? Does my 3? Okay, there we go. And we are getting 326 million people. To Zepha, he went ahead, okay? All right, however, so our model is predicting roughly 326 million people, all right? Let's see what Google says. Yeah, let's go see what Google says, yeah. We're gonna Google it. All right. So if we actually Google this and the internet wanted to actually work. Okay, so check it out. According to Google, and Google is always right, all right? According to Google, what can we see here? We see that the population in 2013 was 316.1. So what do you think, why are we so far off? I mean, what did we get? We came up with this, right? We came up with 326. What do you think, Lauren?
Because between 1970...
Yeah, our model's not that good of a fit, right? Because...
It doesn't always... Yeah.
All right, here's the official U-try. Let me set it up for you so you understand what's being asked of you. Okay, the population of Africa in the year 1990 was 643 million people, according to some data that we have. In the year 2006, it was 906 million people. I would like you to find an exponential model to model the data between the years of 1990 and 2006. So, we're going to talk about the last part of this lesson is all about half-life. And so, the idea behind half-life is this. Everything breaks down over time, and especially like carbon-14 dating and all these chemical processes that they use to figure out how old things are, which is a great process that we have, has to do with half-life, okay? And the idea behind half-life is very basic, right? If you start with some substance, The half-life stuff. If you start with an amount of something, right, and they all have different rates of the half-life. The half-life is how much time it will take for half of that substance to go away. Okay, so um, according to our book, strontium 90. Anyone know what strontium 90 is from the?
Oh yeah.
Yeah, you guys
So
know,
it's
any
like
chemistry out there?
strontium is like 90.
No. So strontium 90 is an element. It's a radioactive element, and it has a half-life of 28 years. So what that means is, if you start with an amount, any amount that you start with, it'll take 28 years for that amount to become half of what it is. Okay? That's what half-life means in layman's terms. All right? So we're going to find an exponential decay model for strontium 90. Now, when I looked up strontium 90 on the internet, the half-life was much shorter, but I'm going to go with what our book says. Our book says 28 years, so I'm going to go with it. So how do we approach this? And this is the key part of this lesson. We start like this. A equals our initial amount, E to the KT. And what are we interested in? Now remember, A naught is our initial amount. And we're interested in half of that amount. Is that true? So how do we set this up? Well, we set this up by this. We say, well, we let our amount to be our initial amount over 2. That's going to be the half-life. Equals initial amount E to the 28K. Now, where did 28 come from? Yeah, this is the key part of setting this up. I'm connecting the fact that 28 years will give you half the initial amount. Because it's whatever amount you're starting with. Half your initial amount. That's what that means. And that's the hardest part for students to understand, is to where to put the 28. Okay, once we've established that this is what we want, then look what we have. Something really, really cool happens with the algebra. If I multiply both sides by 2, here's what I get. Initial amount equals 2 times initial amount, E to the 28K. Does anybody see something else that can be simplified now? Yeah, check that out. Look, you can divide both sides by what? A naught. Look at that. So 1 is now equal to 2 E to the 28K. Oh. Then we can divide by 2. So check that out. 1/2 is now equal to E to the 28K. And the reason is because it doesn't matter how much you start with. Half-life is not required of how much you start with. It just tells you that in 28 years, this substance will be half of what you started with. So it makes sense that the algebra supports the concept of it's regardless of how much you start with. Okay? So now, when we solve this, we're going to say, oh well, the natural log of 1/2 equals the natural log of E to the 28K. Well, so that means the natural log of 1/2 is equal to 28K times the natural log of E is just 1. So I don't need to write that down anymore. And then look, I'm going to divide by 28. Divide by 28. So we're going to plug this into our calculator right here. So K is going to be approximately, and when we do this, ladies and gentlemen, what should we expect to see? A positive number or a negative number? We should expect to see a negative number because we have an exponential decay. So here you go, natural log of 0.5 equals some number, and then divide that by 28, and we are getting negative 0.025 if we round to 3 decimal places. So negative 0.025. So therefore, the answer that we're looking for is this. For strontium 90, according to our book, it's going to be the initial amount, E to the negative 0.025T. Okay, last question of the day here. After how many years will there be 75% strontium 90? Now think about this, okay? So here's years, and here's amounts, okay? So it takes 28 years to get 50%. So I'm asking for 75%. So should your answer be less than or more than 28 years? It should be less than, right? It takes 28 years to end up with 50% of my material. So it's going to take less time to end up with 75% of the material. Does that make sense? So if you had to take a guess, what would be a reasonable guess? Yeah, you'd think it'd be 3/4 of 28, huh? Well, it's exponential decay, so it's not linear decay. Okay? So a good guess, ballpark, I don't know, 15, something right around there. Ballpark, okay? So how do you set it up? Here's how you set it up. You go 0.75 of your initial amount equals the initial amount that we started with times e to the negative 0.025 t. And you solve for your time. Because look, initial amount goes away. Okay? But that's the setup that everybody always messes up by putting 0.75 of that amount. So when you solve this, you get like 11.6 years, which is close to our ballpark figure, right? All right, you guys, there you go.